Hello, my name is Anmol Kapoor, and I'll be presenting my project called CVCars. During this project, I worked on giving an input image, detecting and recognizing the make and model of that car. For instance, in this cartoon character, Lightning McQueen, this is what would happen after inputting in through my putting in through my program. As you can see, there's a bounding box, and then along with the name Lightning McQueen. The general project overview, there are several benefits to using this project. The primary purpose of this project is to detect and find cars in an image. Using this project, like for example, during rush hour, you can see that there's so many cars here. But targeting a specific make and model, you can narrow down that search from finding all the cars in this image to finding just a specific make and model. Like in this, for example, in this image, I targeted Nissan Versa, regardless of the year that it was manufactured. Here's one Nissan Versa, and then here's the second Nissan Versa that could be found in this image. Um, some cost to using this program is that it takes a long, because this was trained using a convolutional neural network, or CNN for short. It takes so much computing power to train the new car image uh, on this neural network, and can take from about half an hour to 10 hours, depending on the number of images and how well you want the recognizer or detector to work, how accurate and how fast. There are several stakeholders for this project. For example, law enforcement and car dealerships. Law enforcement would would use this project to find a suspect car that they are looking for. For example, you often see in your Amber Alerts regarding California Highway Patrol is looking for this Nissan Versa gray color with license plate so and so. The law enforcement can use this program in during rush hour even to to find out where their suspect car most likely is. In addition, car dealerships can use this to find misplaced cars. For example, in a Ford dealership, you might see so many SUVs that look pretty similar to each other, like the Ford F-150, F-250, F-350. Finding a misplaced F-350 among a whole bunch of other cars that look really similar can be hard. So that's where this project would be very helpful. apart The plan for this project was, given an input image, I would uh, first figure out the bounding boxes for each car that in the image, and then from there I would run this through a recognition neural network to determine what is the model of this and what is the make and model of this car. For example, in these three Tesla cars, it would be Tesla. The expected output would be Tesla Model 3, Model S, and Model X. There are several tools that I used during this project. One of them was MATLAB, which is a development environment primarily used by mathematicians and uh, people who need to simulate a model. I use MATLAB for training and executing the detectors and recognizers that I will soon demo. One of the neural networks that I use for recognition and detection are AlexNet and ResNet 50. AlexNet and ResNet 50 are two different convolutional neural networks, and as you can see in this image, convolutional neural networks are pretty much are very similar to regular neural networks, where you are given a graph and weights are computed between each layer to determine uh, some output number. Uh, but the But the layer that's different in a CNN is called the convolutional layer. That's what the C stands for in the convolutional neural network. Here we can see that the weights computed for the to get to the convolutional layer use a convolutional function where given two or more inputs, the weights are computed using this integral function. Two object detectors that I also used were faster RCNN and YOLO V2. Faster RCNN and YOLO V2 are two distinct, both powerful, but different in their own ways, object detectors. The MATLAB console is very intuitive, but at times it can be a bit confusing to handle. To make things simpler, I created two commands, execute RCNN and execute YOLO with their respective detection network. What execute RCNN will do is on a preselected on a set of preselected 5 images, I will run the faster RCNN network, which I have already pre-trained, and then after the faster RCNN network determines the bounding boxes for those cars in the images, it will use the AlexNet classifier to classify what those cars are. There were no cars found in this image, which is a drawback of the detector. The RCNN detector was unable to detect the cars in this image, and one of the cars wasn't detected in this image, but um, as you can see, there's also some errors with the AlexNet classifier. For example, the Tesla Model S was detected as a Mercedes car and the Tesla Model X as an Acura, which is incorrect. And uh, over here, there's no car found. That's expected. That was an expected result. Here, two cars found, but there's only one car listed. For this car, this is definitely a Tesla car, but it was recognized as a Chevrolet Traverse. This is most likely due to the faults within the AlexNet classifier. Now I will run the neural network, the YOLO neural network to detect and recognize the cars in that same set of 5 images. This runs much faster than the faster RCNN, which ran in 32 seconds. As you will see, YOLO runs in about, let's see, 5 seconds. So in this image, you can see that, for this image, you can see that the car was correctly detected, but because I'm still using the same recognizer, Chevrolet Traverse was detected, which is somewhat expected compared to the results of the execute RCNN function. For the next set of images, you can see that one car was detected, unlike the 2 cars in the previous execution. Ford Freestar, although this is not a Ford Freestar, you can definitely see that um, one car was detected and not 2. No car found here, and that is expected. And then finally here, 3 cars were detected. However, the Tesla Model 3 was detected as a Lamborghini. The red car, that's Tesla Model S, was detected as a Toyota Sequoia, and Tesla Model X as an Acura. This is incorrect, and would and to fix this, I would probably have to use a stronger classifier, as with the other images as well. In the last set of images, you can see that several cars were detected and recognized. There were 4 cars recognized in this image. There were several decisions I made for this project, the first of which was choosing a deep learning model. As you can see from this graph and from this line, that as you increase your accuracy, you're going to get slower prediction times. Now, For example, if you're going to use AlexNet, which has about 55% accuracy, you're going to have a really fast neural network. However, with if you want an 80% accurate neural network, about Inception ResNet v2, that's about 10 to 11 times slower than the AlexNet neural network. So for this project, I decided to use AlexNet for my recognition neural network and ResNet 50 for my detection. From the model, from my demo, you saw that I used two detection networks. One was faster RCNN and the other was yellow v2. Fast RCNN is a combination of two networks, fast RCNN and RPN. Fast RCNN searches by a fixed window frame that rolls over your image and and determines the probability of, and for each window frame, it uh, predicts over. It detects whether within this window frame there is an object or not. Whereas region proposal network is builds before the fast RCNN and increases the fast RCNN searching frames by determining a by determining specific regions where there's most likely going to be an object there. For my purposes, you can see that there were cars. Uh, I'm looking for cars. As for the yellow v2 neural network, the one main difference with yellow v2 versus faster RCNN, and most likely the reason why yellow v2 is much faster, is their use of anchor boxes. Anchor boxes are essentially, given the input object that you're looking for, it determines the bounding boxes, the general shape of the bounding boxes, and determines and searches for that same bounding box throughout the image. For example, in a 1x5 image, in a 1x5 rectangular box, it's looking for the side view of a car. From a 1x2, you can see it's looking for the top view of the car. If you're looking head on into the car, that's about a square. So a 1x1 versus a 1x3 or 1x5 anchor box to find these cars in the image. Okay. As you can tell from the demo that I did, speed is so much important, makes the difference between yellow v2 and faster RCNN. With a video, yellow v2 is much faster and can be more accurate than faster RCNN. Faster RCNN is at most about 75% accurate for about 1 frame per second. But with YOLO v2 at around 50 frames per second or 75 frames per second, it's at about the same accuracy. If you decrease the number of frames per second, then you're going to increase the accuracy of the YOLO v2, which is, and for my purposes, for the demo that I did, you can tell that YOLO v2 is about 6 times faster than faster RCNN, running at about 5 seconds for 5 images versus faster RCNN taking 30 seconds for the same amount of images. Thank you so much for watching this video, and I hope you have an amazing day. Thank you.